Consider the following data. We have a classification task where we want to map inputs to either zeros or ones. Logistic regression is a popular approach for these kinds of problems. The model for the binary logistic regression looks as follows. It is a logistic sigmoid, but in this case parameterized with M and B. By default, logistic sigmoid tends towards 0 for the negative inputs and towards 1 for the positive inputs. Let's now see the effect of the parameters M and B. M determines the steepness. Greater the M, steeper the curve, and vice versa. B shifts the function. When B is negative, the function shifts to the right, and vice versa. So to fit the model to the data, we have to determine the optimal values of M and B. This can be done with maximum likelihood estimation. However, likelihood function for the logistic regression is a little different. Essentially, we want our model to predict the probability that the observation belongs to the class 1. Hence, 1 minus the prediction will be the probability that the observation belongs to the class 0. So the likelihood function would look as follows. When the target class is 1, we evaluate the model's prediction, and when the target class is 0, we evaluate 1 minus the prediction. Similarly, the log likelihood function would look as follows. Using this formulation of the likelihood, we can find the optimal M and B using maximum likelihood estimation, maximum log likelihood estimation, or the minimum negative log likelihood estimation. Let's try to approximate the optimal M and B that fits the following data using gradient descent. Because descent is a minimization algorithm, we will use the negative log likelihood. We will start descent with the initial M of 6.8, initial B of minus 15.5, learning rate of 0.25, and a tolerance of 0.3. We want the absolute sum of the partial derivatives for M and B to be less than the tolerance. When finding the derivative, we want h to approach 0, but for simplicity, let's just use a small h. We find a partial derivative with respect to M by applying the previous formula with small h. We can now update M using the gradient descent rule, and the same operations can be performed to update B. Then, we evaluate the partial derivatives for the new M and B to make sure that they are within the tolerance. Let's now observe the resulting plot. The red dots correspond to the data, and the green plot is the logistic sigmoid we just derived. We can see that the plot is steep and it fits the data well. If we round the predictions of this model to the nearest integer, we will get a correct prediction for every point in this dataset.